Hello and welcome to the next demo in our IP Multicast lecture series. This demo will cover PIM Sparse Mode implementation on Cisco IOS routers. Before we begin with the demo, let's cover all of the scenarios that we will be touching in this particular demo. Now, we'll talk about enabling PIM Sparse Mode very briefly, how to just enable PIM Sparse Mode, basic PIM Sparse Mode on all of the routers. We'll talk about how to disable SPT switchover. So the shortest path tree switchover will be covering right at the end of the demo. So during the first few scenarios in the demo, SPT switchover will actually be disabled. We'll talk about static RP configuration, how to configure RPs statically. Now, there are dynamic RP dissemination protocols which we will be covering in a separate set of lectures and demos. But in this particular demo, because we are just concentrating on sparse mode, we'll just talk about the very basic static RP configuration. So nothing fancy here. We'll talk about receivers that are present, but no sources. So there are some receivers that using IGMP have registered themselves with the last hop protocols, but no sources are yet online for those particular groups, and we'll see how the tree manifests itself. We'll do exactly the opposite of this scenario, where there are sources that are sending feeds to the first hop routers, but no receivers have registered anywhere else in the network. We'll talk about scenario 2 followed by scenario 3. So the receiver comes online, registers itself, and then it's followed by the source. The source appears sometime later in the timeline. We'll do 3 followed by 2. So the source is present online already. It is sending a feed, and then a receiver registers itself with the last hop router. And finally, we will touch the topic of PIM's shortest path 3 switchover. So this would be the very last topic that would be covered in this demo. It's time to take a look at the topology next. Now, the topology in this lecture series has also been covered as demo 0. So it's a very short demo, and it's recommended that you go ahead and watch that demo. But for the purpose of this particular demo, a couple of things that need to be noted here. The major network happens to be 172.26. So any of the addresses that you see here, they belong to that major network. So the last 2 octets are notated on the topology. You prepend 172.26 to come up with the IP address there. Also, we'll be using R3 as our RP in this particular topology. And furthermore, we'll be using the loopback address as the RP IP address. Also, every single one of the interfaces, so all of the layer 3 interfaces that you see on this topology, every single one of them, they've all been activated for PIM Sparse Mode, every single one of them. So that keeps things simple, keeps the troubleshooting to a minimum right now. There is no built-in troubleshooting. It's pretty straightforward vanilla topology at this point. When we come to SPT switchover, I'll go over the topology in a little bit more detail, but this particular link between R4 and R7 will then become important. But for right now, all of these links are working at 1 gig. So there are no speed differences on any one of the links. And when we come to SPT switchover, we will see how we are going to leverage something other than bandwidth to demonstrate how the SPT is going to be different than the RPT. But other than that, if you haven't watched Demo 0, now would be the time to take a brief recap of Demo 0, and then we'll come back and start with the demo. Finally, the topology, the PDF of the topology can be downloaded from the link that will appear in the description of the video. So it's also highly recommended that you download the topology and keep it on a separate screen, or basically follow it along as the demo goes along. So that goes a long way. That goes a long way to help work with the actual demo. Next up here, let's quickly go over the format of the PIM hello packet that is used in the Cisco IOS routers. Most of the options that you will see in the hello packet in Cisco IOS routers is RFC compliant. There is one option, however, that is Cisco proprietary, and it sometimes throws people off, so I just want to concentrate on that. So on here, let's look at our PIM neighbors. Do show IP PIM neighbor. And I can see R1 has a neighborship established with R2. That means they should be exchanging PIM Sparse Mode hello messages at this point. And as I also said in my lecture, the hello messages in PIM do not reflect sparse mode or dense mode, so they're exactly the same messages, which also means that sparse mode routers can become neighbors with dense mode routers, and it'll affect the overall operation, but they will think that they are neighbors, and each will operate in the mode that they have been configured to operate in. So in this case, R1 and R2 should be exchanging hello messages. Let's take a look at one of them. So here's a message that is going from R1 to R2. The destination of this message is 224.0.0.13. That is the PIM well-known multicast address. And the source is the IP of the exit interface. Let's take a look here at the actual packet. Also, the protocol is 103. So it's literally wrapped up in the PIM protocol. So next is protocol independent multicast. Version 2, hello type, the packet type, the number is 0. So it's the very first packet. Now there are 5 options contained herein, and 4 of them, options 1 through 21 on your screen, these are all RFC compliant, and they actually are pretty straightforward. So one of them has the hold time in it. It's the same thing as, OSPF dead time or anything else. So if R1 was to stop sending hello messages for a period, R2 will honor this field, or the number of seconds in this field, as the hold time for R1. So it'll wait for a reception of a hello message from R1 for 105 seconds. And if it doesn't receive any messages, then it declares the neighbor dead. So it's basically for neighbor discovery and detection. So it's a TLV, as are all of these options. Option 20 is the generation ID option. This is used for graceful restart. So if the router was supposed to restart, or PIM was supposed to restart gracefully, where the forwarding plane did not cease working, but only the control plane did, across those reloads, this generation ID should change. So it's unique per restart. And as a new hello message goes out of the same neighbor with a new generation ID, now the neighbors know that, one of the neighbors has gracefully restarted, and they refresh all of the S(G) and (G) states as best as they can on that router. So generation ID is how you detect a graceful restart of a neighbor. DR priority is pretty straightforward, so we'll discuss it when we go to the last hop routers, but this is for DR election. By default, it's 1. I believe it's also 1 on Juniper. So as you receive packets over a multi-access interface from your neighbor, you will compare your DR priority to theirs, and the higher priority wins. And if there is a tie there, then you use the highest IP. The next one is actually only specific to PIM dense mode, but it's also included in PIM sparse mode. So we discussed state refresh in depth in the PIM dense mode lecture, and that's where you'll find this information. The last one is 65004. This is for something called PIM RPF vector, or PIM RPF proxy. It is another one of those corner case advanced options that I may not even cover in the lecture series unless there is some demand for it. I've never actually had to use it, but essentially I can show you, if this option was not supposed to be here, what it does. So what it does, if you look on R1 and R2, or specifically on R1, you will see that it detects R2 as a proxy capable router. And the reason it detects R2 as a proxy capable router is because it's receiving that option in the hello packets. So if there was ever a question of disabling this option from hello packets, the command you would use is up here. So you would say or actually it's the opposite of this command. So you'd say IP multicast RPF proxy disable. And that essentially stops advertising this particular option in the hello packets. So the next hello message that goes out should have 4 options. And one of those basically the 4 options would be the ones that you saw. So we'll just have to wait a couple of seconds for that. But apart from that, that is all there is to talk about the hello message. It is sent out, yeah, I'm not sure of the timer of it, but that, again, I'm not a big fan of learning defaults by heart. So as you see, the next packet that went from 12.1, so R1 to R2, does not have that option anymore. So that particular command stops that feature, the PIM RP effective feature, and it disables the sent of that option in the hello packet. So having covered hellos, we can move on to our next topic. So it is time to start covering the scenarios. Let's look at this very first scenario. So this was a precursor to actually discussing sparse mode. One more thing that needs to be done here, and this is more specific to Cisco routers than anything else, just enabling PIM Sparse Mode does not activate IP multicast. So one more additional step here that we would need to verify before we actually proceed is IP multicast routing also must be enabled on every single one of the routers. So this has been discussed in previous lectures and previous demos, but IP multicast routing would be needed to create that multicast rib and to actually start the multicast routing. So that was one part of it. PIM Sparse Mode should be enabled everywhere right now. The other part would be to disable the SPT switchover. So on the very last hop router, so in this case it would be R5 and R6, we would actually go ahead and disable PIM Sparse Mode. I'm sorry, PIM shortest path 3 switchover, and the way it's done in Cisco is you just raise that SPT threshold to infinity. So usually shortest path 3 reacts to the reception of multicast packets over the RPT, and it's actually defined by the rate of arrival of those packets. So when you raise that rate of arrival to infinity, so you're waiting for infinite number of packets to follow down the RPT before you switch over, that essentially means that the switchover doesn't happen. Now this only needs to be done on the LHRs. So we'll keep the configuration to a minimum by only putting this particular command on the LHR. So we'll put it on R5 and on R6. So let's go ahead back to the topology and see if all of this has been done already in our topology or not. So here are all of the routers, and what we will do is we'll move all of these routers into config mode. So I can just send the commands automatically here. And we'll say show run, or do show run in Cisco IOS, include PIM and multicast. And let's see what we have here. So for example, on R1 itself, I don't have IP multicast routing, so I'll have to fix that. R2, R3, R4. R5 actually has that, but R5 also has this extra command for multicast load sharing, so I will be removing that. R6 has the multicast command, so the multicast routing command is a little bit inconsistent here. Now, receivers and the source don't have any multicast or any PIM on it, so they are basically just stubs. So we'll go ahead and put IP multicast routing everywhere. So that should enable multicast routing, or just create that multicast rib structure everywhere. Also, we'll say no IP multicast multipath. This would be discussed in a separate demo. So now all of the routers should have IP multicast routing on them. On the last hop routers, so in our topology, these routers happen to be R5 and R6. So on R5 and R6, right here, so R5 and R6, will also, so these now are the LHRs in this topology. It's going to depend on who becomes the DR. So that would be the next thing for us to check, who becomes the DR. But these are the LHRs, so we also have to disable the SPT switchover on these LHRs. So let's go ahead and do that. So R5 IP PIM SPT threshold infinity. That would actually just disable SPT switchover. And we'll copy this command and also put it on R6. So that essentially means we don't have to worry about SPT switchover, at least for the first part of this lecture. Also between R5 and R6, it's going to be important which router actually becomes the DR. So the DR election here becomes important because the IGMP registration will happen to both of these routers from the end hosts that are signaling IGMP, but only the DR will actually perform the PIM signaling. So whichever out of these becomes the DR performs the PIM signaling. You already know the rules for the DR, and I haven't changed the DR priority here, so it should be easy to guess which one it is. It should follow on the highest IP. It should fall back, the tiebreaker should be the highest IP. So let's go ahead and see if that is indeed the case. On R6, we'll say do show IP PIM interfaces. And the interface that we are interested in is the LAN interface, which is the 56 or VLAN 56. On this one, you can actually see that the DR is indeed 56.6. Another useful command here would be do show IP PIM neighbor. And essentially in the neighbor, you can actually see what DR priority you have, what mode you have. But if you do not see a DR on here, usually means that that neighbor is not the DR. So to see the DR using the IP PIM neighbor command, you actually need to move to the other router, I believe, and you'll say do show IP PIM neighbor. So on R5, you can actually see that R6 is indeed the DR, but you cannot really see it from R6. So either way, now we know that R6 is the DR. So since R6 is the DR, it'll also perform all of the PIM signaling here. So that brings us to the end of, I think, all of the prerequisites. Everything should be working on here. And now let's go and take a look at the actual next scenario. So we have done both of these things. Next is static RP configuration, and this is fairly easy. So you pick an IP. In this case, we are picking the IP that is the loopback of R3. So this would be, in our topology, this would be 0.3. In fact, 172.26.0.3. And you have to configure this command on all of the routers, including R3. Now, one of the things that I've heard from some of the veterans on iOS routers is that you never used to have to do this command on the RP. I can assure you that of late, at least ever since 12.4, that hasn't been the case. I don't remember a case where I didn't have to put this command on the RP itself. So the RP has to know that it is the RP in order to process all of this. And once you feed a local address to it, it essentially takes over the RP duties. So this command would go everywhere. But for right now, just to show what happens with the absence of this command, let's go ahead and commit this command or configure this command on R3, but not anywhere else yet. So we'll just not do it anywhere else yet. We'll do it just on R3. So on R3, we'll say IP PIM RP address 172.26.0.3. Now to confirm if the RP mapping is working correctly, we'll say do show IP PIM RP mapping. And that should tell you, so the RP itself is mapped via groups. So some groups, in order to do load sharing or to do redundancy or high availability, you can match each group to, you can match specific groups to specific RPs. So in this case, because we just gave a completely, a wide command, we didn't specify which groups. In our command, we just specified the RP address. It essentially means that all of the groups, so entire class D, is now mapped to this RP. That's all it means. So the entire class is mapped to this RP. One of the other things that usually comes up is what is the relevance of this question mark, and that really bothers a lot of people. The relevance of this question mark is the DNS lookup. So what R3 is trying to do right now is trying to look up what is the reverse lookup for 172.26.0.3. Since it doesn't have an entry, or I don't have any DNS service configured here, it essentially just says that I don't know what that is. So let's go ahead and fix that cosmetic thing just so it doesn't bother us anymore. And we'll say IP host, I believe at least that was the command, IP host, name of the host, so we'll say R3 is the name of the host, and the IP address of that host is 172.26.0.3. Now if I do show IP PIM RP mapping, it actually does not show the question mark there, it actually shows R3. So right now R3 is up and running. It is the RP. And initially when I put in this command, there were two log messages. There were two log messages for tunnel 0 coming up. So something like tunnel 0 here coming up, and tunnel 1 coming up. Depending on the version of your iOS, you may or may not see these tunnels, number 1 coming up or number 2 there at all. So this has started, I'm not really sure when it started, but I don't ever remember seeing these explicit tunnels in 12.4 at least. So this seems to be a phenomenon of late, but it's actually a good thing. So tunnel 0 usually, now this is, again, I don't have enough use cases to say that for sure, but tunnel 0 would be the PIM Register Tunnel for the sources. So this is a PIM Register Tunnel for all of the sources. And tunnel 1 usually ends up being the register tunnel for the RP. So the sources will send their register messages via tunnel 0, and the RP receives those messages via tunnel 1. So if you remember, the register message is a unicast message, and tunnel 0 and tunnel 1 are just data structures that help you process that message a little bit better. So really, if we look at these, they're fairly simple. So I'll say do show run int tunnel 0. Now this should be the source tunnel. So if you look at it, there's no configuration on there. Neither is there any configuration for tunnel 1. But if I say do show IP int, so look at the actual relevant configuration of it, or what it is working off of. So here, the interface is unnumbered, and it is using the address of gig 23. Now this, I believe, can be changed by a command, so you can decide which local address are you going to use in the unicast as the source IP of the unicast packet. So there is an IP PIM register something command, it's a source command. So you can change that, but by default, it's essentially going to pick the exit interface. Now, because we are on the RP, it's a little bit confused because I think it basically just picks an interface. Anyway, tunnel 0 here is sort of irrelevant, right? Because you're on the RP itself. The next thing to see here is, so it does say somewhere, well, actually it's a different command to see this, but you can see anything else, there's nothing really going on here. All of those things just look either disabled or not set. But if I say do show int tunnel 0, it should show me that number 1, it's a tunnel encapsulation, but the description is the encapsulation tunnel for register. So this is the tunnel you would use to encapsulate register messages. So again, register messages are a unicast concept. They are a tunnel concept because we are also tunneling those multicast packets inside the unicast tunnel. And this is the register tunnel for that particular RP. So to send register messages or to tunnel multicast messages via register messages to that particular RP, this is the tunnel that's going to be used. Once again, the interface is unnumbered. This is the source IP. The destination IP here is not given, but because it is this RP, I'm assuming that's how it... Actually, I take that back. Here's the tunnel source, and here is the tunnel destination. So if you were configuring a GRE tunnel, this would be, you know, those tunnel source and tunnel destination commands. All of this is being done for you automatically. So it's just a structure. And again, depending on the iOS version, you may or may not even see this. But on the latest ones, it's definitely there. And finally, it does say somewhere that it is an encapsulation tunnel. Well, I guess this is all it says. So there is a tunnel protocol mechanism somewhere too that says, well, it's PIM and IPv4. So that's the tunnel protocol. So it's not GRE, it's nothing else. It's actually just PIM because it's for register messages. So tunnel 0 here was the encapsulation tunnel. That means tunnel 1 should be the decapsulation tunnel. So tunnel 1 here is the decapsulation tunnel, and it's again for one of the local addresses. Now the tunnel source is irrelevant here, right? Because it's really a multi-point to point tunnel. The sources could be any of the FHRs or the first hop routers in your topology. So the tunnel source here doesn't really even matter. But I believe it's just using the loopback IP as a placeholder. So this should really be any address. The destination is the local IP that is playing the role of the RP. And everything else is same. So if you look at the tunnel protocol, it's PIM and IPv4. It is sourced off of loopback 0, so all of that good stuff is here. But really, this is just a data structure that you're using. It's an abstraction. So it's an abstraction of those PIM register messages. One important thing to remember here, though, would be where would you see 2 tunnels and where would you see 1 tunnel? On all of the other routers, so all of the non-RPs, you should see 1 tunnel per RP. Because like I said, the RPs doesn't necessarily have to be 1 RP. There could be multiple RPs for different groups. So depending on those, in our topology, for example, there's only 1 RP right now. So you should see 1 tunnel interface on all of these routers. So if once we do the RP address command there, we would see 1 tunnel interface on all of these routers. But on the RP itself, because you need that decapsulation tunnel, you would see 2 interfaces, which we have already ascertained that there are 2 interfaces here. So just keep that in mind, and this only happens with the latest iOS routers. Now let's look on R6, because R6 is our DR, so all of the last hop signaling is happening off of R6. On R6, let's say do show IPM route. And it looks like this auto RP IP is here. So in future, anytime you see 224.0.1.40, till we do the lecture on auto RP discovery, it's going to be irrelevant. So don't worry about that right now. But other than 224.0.1.40, I don't see any other groups. Well, let's make sure if any groups from the last hop routers have actually joined. So from Rec 100 and Rec 200, has any IGMP signaling been done? So let's say do show IP IGMP groups. And right now it looks like I have no signaling happening. So what we will do is on Rec 100 and Rec 200, because what we need to do next is, well, we are going to come back to the static RP configuration, but the next scenario here is receivers are present with no sources. So let's see what happens. This is one of the common troubleshooting scenarios. So I'm sort of building it in here. Let's bring the receivers online, but not configure the RP address just yet. And let's see what happens in sparse mode when that happens. So on Rec 200 and Rec 100, let's look at what's happening on the interfaces. Do show IP anti-brief. Now, if you looked at demo 0, you would realize that these are just plain simple iOS routers. But There is no multicast routing on there. Well, right now there is multicast routing because I put in a blanket statement there. So let me take that out. So no IP multicast routing. And also no IP unicast routing. So these are just stub routers with the default gateway. So if I say a do show IP route on here, you just see that we are using a default gateway, and we would use either R6 or R5 as one of the routers. Now this is to reply to those multicast messages. It's for unicast IGMP echo replies for our testing. But really it doesn't matter. And because of my environment, I wasn't able to get HSRP or VRRP running on it. So we just decided that Rec 1 was going to point to R5 and Rec 200 was going to point to R6. But really there is nothing on here. Let's look at the interface itself. Do show run int g00.56. And once again, there is nothing here other than that VLAN and the RP address. There is nothing here. So one of the first things I'm going to do is actually join a group. So we'll say IP IGMP join group, and let's join 239.1.1.1. Let's also look on Rec 200. So same thing here, do show run include routing. And there is multicast routing here that I would like to take out. So we'll say no IP multicast routing. There's already no IP unicast routing, and do show IP route shows you that the default gateway is simply 56.6. Now let's look under the interface. Do show run int g00.56. And there are no groups joined yet. So let's go ahead and join a group here as well. So we'll go to this and we'll join IP IGMP join group 239.2.2.2. So now there are two groups that have been explicitly joined from the LHRs, or sorry, from the receivers on the last hop segments. On R6, let's confirm. So we are receiving that signaling on R6 now, 239.111, 239.222. So because R6 is the DR, now there should be some, theoretically, there should be some PIM signaling happening for the star comma G tree. So we will say do show IPM route. And if you look at it, there is no IIF for either one of these. There are interfaces in the OIL for both of them. So G056 or VLAN 56 is in the outgoing interface list, but neither one of them actually has an IIF. I'm sorry, I'm looking at the wrong one here. So we should be looking at 239.111 and 222. But either way, you see that the IIF is empty. And because the IIF is empty, usually a culprit would be no RP. So the router doesn't really have an idea of what the RP is supposed to be. So if I say do show IP PIM RP mapping, the mapping is completely empty. So it doesn't really know where to send that star comma G join. So if we were to look at the packet capture right now, you would see no star comma G joins. So let's go ahead and bring that packet capture in. And I'm filtering it for all PIM messages right now. So it's being filtered for all PIM messages, but as you can see, all we have in this topology right now are just hellos. There are no star comma G joins happening at all. So without the idea of an RP, it's really impossible for the LHR to even construct that message. Because remember, there's going to be the RPT bit, the wildcard bit, but most importantly, in the S comma G portion of it, in the join sources, you need to put the RP's IP in there. And if you don't have that IP, then the process doesn't even start. So that was one of the scenarios that I wanted to cover here. Now let's go ahead and on all of these routers, let's put that RP address in there. So we'll say IP PIM RP mapping or RP address for static RP address 172.26.0.3. Now as I put this in, the packet capture should now start seeing some joins, again theoretically. So there we go. We see a whole bunch of join prune messages, and because join prune messages are hop by hop messages, I should just see a single join prune message that is going hop by hop from R6 to R5, Actually R5, now there are a whole bunch of joins for that 224.0.1.40, so those need to be ignored. But it should really go from R6 to R4, from R4 to R3, and then that's it. So it should terminate in R3. The other join prunes that you see here, unfortunately, are that 224.0.1.40, and that's, whenever you're working with Cisco routers, that's going to happen. So let's look at this join message. As I told you, so R6 happens to be the LHR. There are 3 separate groups that are in here now that are being signaled for. So you have group 239.222 and 111, but you also have that other group. So we'll ignore the 224.0.1.40 for the purposes of this lecture. Let's peek into one of these other groups. So the ones that are interesting to us. So for 239.222, there is one join and no prune. So can you guess what would be the source IP of this join, or the S(G) portion of it? So let's expand the join, and you see that in the source is the RP's IP address, and that is how you are getting the reverse path forwarding check done. But in order to signal that this is still a *G join, going to an RP, because you're leveraging the same message again. So these 2 bits, the wildcard bit and the rendezvous point bit, are both set here. So the wildcard bit, the W bit, is saying that this is a *G join, and the R is saying that this IP actually happens to be an RP's IP. So both of those fields together, both of those flags together, now essentially route this message correctly through our network hop by hop. So let's go ahead and take a look at the actual mroute table on R6. And once again, you see, as I put the RP address in, that tunnel 0 came up. So this is now the encapsulation tunnel. And, we've covered that now. So we'll say do show IP mroute. And there we go. Now we have IIFs, or incoming interfaces, for both of these groups. In fact, we have them for all 3, but just kindly ignore that. So we have a *G entry, complete entry, with an IIF, with an outgoing interface list for 239.111. We also have it for 239.222. Now the RPF neighbor here happens to be 46.4. So let's go ahead on to router 4. And we'll say do show IP mroute. And again, on the middle hop routers, it's absolutely necessary for you to have the same ID of the RP, because it's going to receive this message. It has to be able to, number one, see that they share the idea of the group to RP mapping, because here's the group, here's the RP, courtesy of that R flag. So this group to RP mapping has to match across all of the middle hop routers, because they have to process this message. So in this case, it will match. And for 239.111, the RP is 0.3. For 239.222, the RP is also 0.3. And that's it. So the RPF neighbor now is 34.3, which is router 3, which should be the RP. So on the RP, you should see a *G entry, but without an incoming interface, because this is the root of the *G tree. This is where the *G tree ends. So do show IP mroute. And there we go. The incoming interface here is null, but that is not a bad thing here. This is the root of the tree, and that message is, or that information is contained herein. So RPF neighbor is 0000. That doesn't mean an unknown address. In this case, it means the local IP. So the RPF neighbor, I am the RPF neighbor. That's what the RP is populating the entry as. So RP actually happens to be its own RPF neighbor, because it hosts the 172.26.0.3 address locally on itself. So at this point, if you look at the *G tree, the *G tree is actually complete. It goes from, and one more thing. So let's look on R5. If R5 is trying to do any signaling, we'll say do show IP IGMP groups. to make sure that the groups were signaled here. So both of those groups, 111 and 222, are both signaled here. But when I say do show IPM route, there is nothing in the oil. So there is something in the RP, in the incoming interface, but because there's nothing in the oil, it's a pruned group. So if you look at the flags here, P is pruned. So essentially, because it's a non-DR on the signaling interface, so where the IGMP signaling is being received, which is gig 56 right here, because it's not the DR, it's the non-DR on that segment, it's essentially just going to keep that group in a pruned state. And the reason for keeping it in the pruned state is what happens if the DR goes away. If the DR goes away, then R5 will start the actual signaling. But if we look again at our packet capture, there is a message from R5, so 45.5, but it only has that 224.0.1.0 address. So number of groups 1, and this is the only group. So the non-DR does not do any PIM signaling at all in PIM Sparse Mode. It's just silent. So back to the topology, and now the star comma G tree is completely established. It is established from R6 to R4 and R4 to R3. So this is your star comma G tree. And this is what would happen if there are receivers, but there is not a source. So for both of these groups, there are receivers present, but there is no source. So some of the things that you have to pay attention to here, we'll cover a lot more of this in the troubleshooting sections as well. But some of the things that are important here is what does the DR versus the non-DR concept do in PIM Sparse Mode. So now it should be pretty apparent that that is an important concept. It's not like dense mode. What happens when you configure the RP addresses on modern Cisco routers, the whole tunnel concept. So those are some of the things that we would need to keep in mind. Other than that, we are ready to move to the next scenario. The next scenario is exactly the opposite of the last scenario. So the last scenario here, number 2, was that receivers were present, but there were no sources in the network. Now, there would be sources present in the network, but there are no intended receivers. There are no receivers that have shown any interest in receiving the stream that the group is multicasting on. So for this particular scenario, let's pick a group. So our receivers present with no sources, if you remember, those were groups 1.1.1 and 2.2.2, both of them prepended with 239. In this case, sources present with no receivers. Let's work with group 333. So 239.333, that would be our group. And there would be a receiver, there would be a source, the source sending IGMP packets multicasting to this group, but there would be no receivers at all present in our particular network. So let's go ahead and take a look at this. So in this case, what should happen here is that the source should actually send packets out over here. So 239.333, the packets would go in over here. The reaction for the first hop router, the FHR, this is the first time that it has ever received any packets from this particular source on that particular group. So it should go ahead and create that S-G entry. And once it creates the S-G entry, it should look for that tunnel interface to the RP, or literally look for the RP's IP address. It should take that packet, it should take that IGMP packet, and it should then unicast this over, or tunnel it over to the RP. Once the RP receives it, the RP should also create that S-G state. And because there are no intended receivers right now, there is no star comma G entry that matches this group, it should almost immediately respond with a register stop message. Now in our packet capture, there's a caveat here. So in our packet capture, what I am actually doing is I'm capturing packets on all of these sub-interfaces at the same time. So what we should see and what you should be aware of when we are looking at that is that the register message would be captured on two interfaces. So the register message would be captured on this VLAN 12 and also on VLAN 23. But it's the same exact register message. We're just capturing it twice. So in my packet capture, you would just see it twice. The same thing for the register stop. So once we go into that, just keep that in mind. Other than that, let's go ahead and start sending some packets out. What I will do right now, I'm not going to bring this into a steady state. I will send a single packet so we can actually see the register message go out. We can also see the packet encapsulated in that register message, and we can see the register stop. But after that, what I want to see is I just want to see null registers, right? So this is not going to be a steady state just yet. It's going to be a single packet, and we're going to see how the entries are going to be expired. So we'll say simply ping 239.3.3.3. And by default, iOS will just send one single ping out. Let's look on R1. So R1 is our FHR. So on R1, there should be that star comma G entry now. So let's say do show IPM route. And we're going to qualify it with 239.333. So here we go. We have that S comma G entry. Just ignore the star comma G entry while I circle back to it, but there is an S comma G entry. There is an incoming interface, so there's an IIF. Now this is the IIF that is facing the source, right? So this would be that IIF. The RPF neighbor is 0.0.0.0. Once again, it doesn't mean unknown address in this case, it means our local address, it means myself. So you are your own RPF neighbor, that means you're the point of origin here. Other than that, this is T, so there is a shortest path tree concept here, and I'll explain this in a little bit more detail, but for right now, this is not an actual bit that is present in the register message or anything else. This literally is a state on the local mroute or local PIM table that says that you have received some packets on the S comma G tree. That is all that it means. So there is no bit in any of the PIM messages, but this SPT bit concept essentially just means that you have received some packets on the S comma G tree, or you were able to create an S comma G state there. The flag F here is the register flag, so that means you have been able to successfully register with an RP. Now, where is that RP information? So when you look at this, you also see that star comma G tree. There's only one real reason for the star comma G tree to be here, and that is as a placeholder for the RP information. So when you look at the star comma G tree, the only useful information in here is the ID of the RP. What is the RP to group mapping for this particular group, for 239.3.3.3. That is contained in the star comma G tree. So just like with dense mode, you had a star comma G tree that was a container of all of the oil. This essentially is a container for the RP. There is nothing else here that really is of any importance. If you look at the flags, SPF, so it's sparse mode. It's also pruned, which really, what do you care? There's no receivers here, so star comma G should be pruned here. There's no interested receivers. And as we looked at it, F is register flag. So there you can do registration to this particular RP. But when you look at the first hop router is expecting to see only an S comma G tree, and you see a star comma G tree as well, just remember that it's there as a placeholder for the RP itself. And there's really nothing else. In fact, if you look at the incoming interface here, it's just an RPF interface to the RP. So they're playing the whole game of joining the star comma G tree, because if you realize if there was an actual source here, so if there was an actual, if there was an actual receiver here, and you received an IGMP join here, so you received an actual IGMP join here, and created a star comma G as a result of that, what would be the RPF interface? It should be the interface that is pointing to the RP. And that is what you see here. So you do see that interface, gig 012, VLAN 12, as that. But really, it's pruned. Because there are no sources, this tree actually is pruned. So really just a placeholder for the RP, but it does throw a lot of people off. So it's worth mentioning. Now on the RP itself, it should have received a register message, and it should have created an S, G tree for that. So let's take a look at that tree here, show IP M route. And this should be 239.3.3.3. So at this point, there is a star comma G entry for it, which basically means that our registration probably has timed out. So let's take a look at this again here. And that registration has timed out because it wasn't in an actual steady state. You weren't receiving actual messages on it, or consistent messages on it, because if you look at it, the source sent that one ping and then it kind of died out. So all the while I was talking, that registration state was expiring. But we should have been able to capture it on the packet captures. So let's take a look at what happened on the packet captures when it came to registers and register stops. So register and register stop messages are PIM type 1 and PIM type 2. And this is exactly what happened. So there was that first register message that went out. And if you look at it, it's colored differently. So already I can see that it's not being treated completely as a PIM packet, because if you think about it, what is a register message? The register message is a unicast message, correct? In this case, what is the destination? So the destination for this message looks a little bit weird, a little bit awkward. It doesn't look like the destination that I told you. That's because Wireshark is trying to be extra helpful here. So let's take a look at the IP protocol packet, so the IPv4 header here. And in the IPv4 header, the destination is actually unicast. It's 172.26.0.3, and that is exactly what we would expect to see here. 172.26.0.3. And that's correct. But what is contained inside this packet actually makes a little bit more difference. So this packet actually contains first a PIM header. So the PIM header itself, it's a register message, so it's type 1, which is a register message. It is not a null register message. That means it doesn't contain a dummy header. It actually contains a real, actual live multicast packet. And if you go further along, you actually see that packet. So it's an ICMP packet. So to contain that ICMP, first there would be that full IP protocol header. So there you go. In that IP protocol header, now the destination actually happens to be 239.333, because this is the original ICMP packet that was sent by the source to R1. And you can see here, the protocol itself happens to be ICMP. The TTL looks correct. It has been decreased by 1. The source and destination look correct. This is the S, and this is that G. So both of those look correct. And finally, when we go into the so let me see if I can get this correct here. I really can't, so I'll just wipe it off. And if I look at the actual ICMP message, I can see that it actually contains that echo. So it has that echo, it has a sequence number, it has the actual data ABCD, ABCD, ABCD that was sent by my first hop source. So that packet was tunneled all the way inside a PIM register message from R1 to R2, to R3, the RP. And the RP responded with a register stop message. Now the register stop message is much easier because it doesn't really contain any tunnel concept in it or any tunnel packet. Wireshark actually does report this quite correctly. So it is reporting it as a source of the RP and the destination of the first hop router. So it's literally the reverse of the source IP and destination IP fields that would be in the register message. There is that PIM header down here. The PIM header identifies that this is a register stop message. And finally, in the PIM option, so this is not a dummy IP header, this is not an IP header at all, because the structure of the register stop is inherently different than the register message. All the RP identifies is the S, G. So here is the S, and here is the G, and for that, this PIM register stop message should really be processed for that S, G. And that's it. So with a single packet, that's all we saw. We saw one registration, one register stop, and after that, the phase just timed out. So the state itself timed out on the routers. Now let's bring this into a steady state. One of the things I wasn't able to show you here because we only looked at the outputs of the FHR and the R3, so we never actually looked at the output of R2. But essentially that would have been uninteresting anyway, because these messages sort of tunnel through R2. So the register message literally tunneled through R2 over to R3. There would have been no state in R2 at all. But once we bring this into a steady state, I'll show you, but essentially there should be no PIM state or PIM state for that particular group on R2, because R2 never actually processed that message. It just sent a unicast PIM message through itself. So it forwarded that message. It never actually processed that message at all. So now let's send a steady state. I'll just send, say, 10,000 of these. So we have a steady state going. There should be no replies right now, but there should be a constant stream of IGMP packets in our system right now. So let's go back and look at R1. And let's look at the show IPM route for 239.333. This is the same exact thing that we saw that first time. There is an S, G entry right here. And there is an incoming interface. And there has been registration. So that F flag is very important, that we were able to actually register with the RP. And there is no outgoing interface list because really nobody has joined that S, G tree yet because there are no receivers in our network. On R3 now, we should see an S, G state. So now there is an S, G state on R3. It is pruned because you really have no receivers again. So that prune essentially means that you never bothered actually building the S, G tree out because there were no interested receivers. The incoming interface should be the RPF interface towards the source. So this should be the interface between, this should be this interface. That is the RPF interface back towards the source, and that is what it is, 23. And there is a star comma G here just to essentially carry that I am the RP. So it's again a placeholder. So when you have an S, G, you will have the star comma G as well. So the same concept applies. It's identifying itself as the local RP, but when you look at the RPF neighbor, it's 0000, so that means the local router happens to be the RP. Once again, this is a sparse mode group, and it is in prune state. So all of that kind of brings together. But yes, most of the times in Cisco IOS routers, when you see an S, G entry, you'll also see a star, G entry, which will provide you further information about that group. But really, there is no traffic flowing here right now. Now, let's also look on R2 as basically it's a cursory thing. So we'll say do show IP mroute 239.3.3.3, and we see nothing. So there is no state for that group. Let's look at the whole multicast routing table here. Do show IP mroute. And there's only that 224.0.140 auto RP group, which we will talk about later. But there's really R2 right now is not involved in this process at all because it's a tunneling process that is happening. Let's also look at our packet capture now. So on this packet capture, if you look at it, look at the difference in the number of the packet and the timestamp. So really this is a brand new register message that went out. And once again, the concept of this register message is the same. So I'm looking at that first register message that was sent by R1 to R2. So it was captured on VLAN 12. And in fact, both of these are exactly the same like I explained before. But it's protocol independent multicast. It's not a null register message. It contains an IPv4 header inside, identifying the source and the group, so the S(G) here. And finally, it has that actual IGMP echo message that is tunneled inside it. It was responded to by the RP with a register stop. So the register stop identifies the group that it wants the LHR to stop sending registers for, put itself in a timeout. That timeout expires, so whatever is the expiration time for that, and it looks like it's about, about 130 seconds here? So in 130 seconds, it expires, and the FHR R1 is going to send another PIM register message, but this one is actually a null register message. So the first message was the actual tunneling message. So this contained IGMP in it. But this register message is actually a null register message. And with the null register message, what you will see is, number one, you would see this flag in the PIM option. So it is a null register. It's actually identifying itself as a null register message. But when you look at the internet, the IPv4 header, this is actually a dummy header. So the total length is 20. That means it's barely just, it's just the IP header. There's nothing in the body of it because the header length is 20, the total length is 20. So that means it's just the IP header. The time to live is 0, right? So that essentially also identifies it as a dummy header. The protocol is not IGMP. The protocol this time is PIM. So it's once again to give more information that this is indeed a dummy header. There is no header checksum, so it's unverified, and there is a source and a destination. So this is basically just to keep the state of the S(G) alive. That's all it's doing. It was responded to with a register stop message, and then that process happened 120 seconds later again. So it seems like 2 minutes is about the timeout, with give or take a little bit of variation in there to stop synchronization. But other than that, register, register, stop, and this should continue every 120 seconds. So that's literally what is happening here. And like you see here, so once again, there was a register and a register stop. And that will keep on happening till we don't actually bring an actual receiver online. So this would keep on failing. And the state would just be kept on R3, which is the RP, and on R1, which is the FHR. So even the middle hop router R2, just to make sure one more time, it doesn't have any state at all. And that's a pretty decent idea that either something has gone wrong with the build of the S(G) tree, or something has, basically there are no receivers. But this is all that is there to it when there is a source present, but there is no receiver to actually demand any multicast stream from that source. You would just see those empty S(G) states on the FHR and on the RP, but that also tells you that the registration process, at least from an FHR point of view, is working well. It's it's actually doing its job. And if you look on the RP, then the RP is also registering. So the RP is accepting the register message by creating that S, G state. The FHR is doing its job by actually informing the RP of an actual active source. And finally, the register stop, and they keep playing that dance again. Keep in mind with the iOS routers that the S, G tree is most often accompanied by the star, G tree, and you can find that extra information in the star, G tree. What we will do at this point is we will bring part one of this demo to an end, and the other scenarios, especially this next one, which is receiver comes online followed by the source, so 2 followed by 3, and the rest of the scenarios we will cover in part 2 of the video. So stay tuned for that. As for this video, we'll bring this one to an end.